Okay, so this is the last chapter. It's the last stage of our semester, and it's about Laplace transform. So it's also for Laplace transform. It's also for solving differential equations, and it's very powerful tool that you can solve much broader types of differential equation that we covered so far. So what is Laplace transform? So it is defined in a weird way. It's using an improper integral. So if you have a given function f of t on on the interval 0 to infinity, then the Laplace transform is another function about variable s, whose value is defined to be the value of improper integral. So as we learned about improper integral, this has to be exist. The limit has to be exist in order to have a Laplace transform. But there is a theorem that if a function satisfies certain conditions, then the Laplace transform always exists. And we're not going to dive into that subject. We'll always assume that what we are considering in this semester is a function that is able to Laplace transform. And also, you might notice that there is a weird adjective here, that our function large f of s is defined to be a complex number. So you might think this is weird because we integrated a real valued function f of t. But how do we get a complex function f of s? So the key point is our s that we plug into the exponent of e is complex number in general. So it doesn't have to be a real number. So reason why is that this Laplace transform actually is a special case of Fourier transform, and Fourier transform is defined on the complex plane. And we're not going to go deeper into that subject also. That will be covered in the complex analysis course in second year. So our purpose is to get the nice feeling of what this Laplace transform is, and also the formula, how to apply the formula of Laplace transform. So from now on, we are going to write our Laplace transform in two different ways. So one way is that if you want to specify the function that we are going to Laplace transform as small f of t, then we are going to use this L f of t, meaning that it's a Laplace transform of the f of t. And if it's clear that what we are talking about as a Laplace transform, then we just simply write as large f of s. Okay. So we differentiate the variable of Laplace transform and original function. So original function is a function of t. Laplace transform is a function of s. This s is a variable for frequency. So in a Fourier transform, what Fourier transform does is that it transforms the function of time into the function of frequency. And since Laplace transform is a special type of Fourier transform, we use the similar rotation. So that's necessary knowledge for now. And the easiest proposition is that if you have a linear combination of two functions, then the Laplace transform of that linear combination is the linear combination of Laplace transform of each functions. So this Laplace transform is linear. So this is an easy examples of Laplace transform. And one of the most easiest part is the Laplace transform of polynomial. So more specifically, if we can find the Laplace transform of power functions, then we can transform the polynomials because of the previous proposition. And this formula works also for 0, n equals to 0, 1, 2, 3, and 4, and for all positive integers. So let's try to prove this. I'm not going to prove every cases, but I will show you why this is true. So let's take the simplest case when s is n equals to 0. It says the Laplace transform of 1 is equals to 1 over s, right? 0 factorial is 1. So let's try to define the Laplace transform. Here we have e to the minus st times 1 dt. So that's the Laplace transform of 1. So I have 1 here, right? Now if you follow the rigorous definition of improper integral, you have to set the limit of integral from 1 to b, where b goes to infinity. But I'm not going to write that out, assuming that we all know what that means. So simply write it as, take the antiderivative of e to the negative st in terms of t. I have minus s and e to the minus st, right? So and then simply write as 0 to infinity. So when I write this, I'm not plugging infinity, I'm just sending t to infinity. So when t goes to infinity, so assuming that s is a real number for now, although I told you that s is a complex number in general, assuming that s is a real number, what happens to here is, and also s is a positive real number, what happens to here is that when t goes to infinity, this goes to 0, right? And this also this is constant. So assuming that s is positive real number, then so when t goes to infinity, this all becomes 0, and when t goes to 0, then this becomes 1. So this is minus 1 over s. So this is 1 over s. And that's how we got the formula. Now we have an assumption that this is not the correct computation when s is complex number, although I didn't tell you how to take a complex exponent here. But this works. So whenever you compute the Laplace transform, you have to assume that your s is a positive real number. So that's how Laplace transform actually defined. So most of the mathematical statement is very rigorous, but here we're not taking it too rigorous, because what we are going to do after all is to take the inverse Laplace transform and coming back to the original functions. To retrieve the original function means that I don't care what happens in between. Although I assume that s is a positive real number, s can be any number, so I can just simply pick one number that fits the best and then use it when I retrieve the original function. So you see what I mean after the class. And let's take about so let's use the induction method. So let's assume that L of t to the k is defined to be s to k plus 1 k factorial for k. So suppose that I show that this is true for all k less than n. And I want to show that L of t to the n is the formula that described here. So let's try to integrate, use the definition of Laplace transform, e to the minus st times t n dt. So I'm going to use the integration by parts. First, I'm going to take an integration and here derivative. So we have minus s e to the minus st times Tn, and here we have 0, infinity, and then minus of minus, so it's a plus of 0, infinity of the s e to the minus st times n e to the t to the n minus 1 dt. Okay. So here n is bigger than 1, so because I already showed that n equals to 0 case is okay, so I'm assuming that n is bigger than or equal to 1, so this is not 1. So when I plug in t, it becomes 0 because of this one, and when I plug in 0 because of this term. So all becomes 0. So this disappears, and here s and t are constant, so let's take out this n over s and integrate this e to the negative st t n minus 1 dt. But this is the Laplace transform of t to the n minus 1, right? N over s of Laplace transform of t n minus 1. And we assume that the Laplace transform of power function whose exponent is less than n follows this formula. So we simply plug in the formula here, n over s times n minus 1 factorial over s n minus 1. So therefore, I get Sn and n factorial. So this is the formula that it's given in the proposition, and the induction method, we know that this is true for every integer n. So any questions? Okay, let's keep looking at the proposition. So, 또 끊겨요? 잠깐만요. Okay, so let me fix one. Let me fix the lagging first. Let me fix it. 잠깐만요. Okay. I'm sorry. Yeah, that was a mistake, and I applied the formula. So, yeah. So this one, we have Sn, right? Because of the k plus 1 formula. Sn. Yeah. So we have n plus 1. Okay. Right. So let's look at other formulas. So for your information, I will give this formula in the midterm, so you don't have to memorize everything, but you have to understand how to apply this formula. So think about the Laplace transform of the exponential function e to the at. So a is the coefficient of t, and that becomes the shifting variable of 1 over s. Okay. And if you Laplace transform sine or cosine or hyperbolic sine or hyperbolic cosine, you get these formula. So sine and cosine is simply derived from the integration of parts, and also hyperbolic sine, hyperbolic cosine can be derived from this method. So hyperbolic sine is e to the kt minus e to the minus kt. So Laplace transform of that is given by 1 over 2 of Laplace transform of e to the kt, 1 over 2 times Laplace transform of e to the minus kt. And so this is by previous proposition, that the Laplace transform is linear. And use this formula, the second formula here. So we have 1 over s minus k minus 1 over 2 times 1 over. So we have minus k here. So this is s plus k. So if you combine these two formula, you get this. Okay. All right. So that's it. And also very important part of the Laplace transform is that you can transform a step function. So not every function is defined to be as a polynomial or sine or cosine. In a real life, there's a situation where the external force or external terms might not exist at a certain amount of time, and then certainly the switch is on afterwards, and then the external force applies to the system. So in that case, we have to use the step function defined as u. So this u is written as u of t minus a. So basically, it's a shifting of u of t, where u of t is a 0 or 1 function. 0 when the negative side, 1 on the positive side. So when I shift my function ut to the right by a, then this becomes u of t minus a. And then this function is 0 when t is less than a, 1 when t is bigger than a. It doesn't matter when t is a. It could be defined to be 0 or 1 because it's not a continuous function after all. And integration, when you take a Laplace transform, it's okay to be discontinuous at certain finitely many points. So, but usually we define to be 1 when t is equals to a. And also notice that we only define t from 0 to infinity, because in the Laplace transform, we always considering the function to be defined on the positive interval. So when you have a function f of t and you multiply this f of t minus a with u of t minus a, then the Laplace transform of this product function is given by this e to the negative as times fs. So this is a very important proposition, because many students are confused to use this proposition, this formula properly. Do we have so we don't have an example. So let me give an example here. So suppose that we have a function So we have f of t sine t. Then how about Laplace transform of u of t minus pi? So what is this? So there is no formula to apply to this Laplace transform directly. What we all know is the Laplace transform of t minus pi times u of t minus pi. We know that this Laplace transform is e to the minus pi s times f of s, where f of s is now Laplace transform of f of t, right? So e to the minus pi s times the Laplace transform of sine was plus. So we have s squared plus 1 over s. Okay. So how do we solve the first examples in here? How do we get this? So I have to change my function. So let's say we have So what happens here is it's a Laplace transform of sine t times u of t minus pi, right? So this one is this function. And I want to rewrite that in terms of sine t minus pi. The reason why I use sine is that if I shift my sine by pi, it's still a sine function, but the sign changes. The parity changes. So it becomes negative sign, right? When I move my sign to the right side, it becomes a negative, right? So we have times u of t minus pi. So what happens? We have a negative outside and sine t minus pi times u t minus pi. So therefore, it's a negative of e to the minus pi s squared plus 1. We have a minus sign here. Okay? So this is actually the hardest part or tricky part of Laplace transform, but also it's a fun part of Laplace transform. There is a lots of trick to transform the Laplace, make a Laplace transform. And so think about the step function again. If, so we have a we have a function in t, so this is y. Let's say I want to make my function to be pi over 2, and then after waiting about 5 over 2 unit of time, I want to make my function to behave like a sine function. Okay. So I don't care about when t is negative. When positive, it's 0 until t goes to pi over 2, and then it behaves like sine function with amplitude 1. So how do we write this function in terms of the sine and the unit step function? So here's a candidates. So one candidate is that y is equals to unit step function t minus pi over 2 times sine t, or second candidate is that y is u t minus pi over 2 sine of t minus pi over 2. Which one is correct? 1 or 2? 끊겼지? Which one is the formula of this graph? Yes, 2 is the formula. So if the graph is given, it's easy to write the formula. Suppose that it is already given as, so when I shift my sign, it becomes a negative of cosine, negative of cosine t. So suppose that your function is given in this form. So if you take the Laplace transform of negative of u pi over 2 times cosine t, then you have to be able to transform your formula into this form and then apply the Laplace transform there. So this is negative of Laplace transform of u of t minus pi over 2 sine t minus pi over 2, right? So this is negative of, use the formula. So we have e to the minus pi over 2s over the forgot the formula here. So cosine Laplace transform is yes, okay. So we have sine s squared plus 1 times s. Okay. So although we have a cosine, I'm not using the Laplace transform of I'm sorry, so sine. So what am I doing here? So although we have a cosine, so we don't use the Laplace transform of cosine. It's a Laplace transform of sine. Okay. So that's a tricky part of Laplace transform. So any questions? Okay, so now we are ready to talk about the direct delta function. So it's a limit of combination of two step functions. So let's define our delta A to be function defined as follows. So if I graph this function, it's obvious what I'm talking about. So at centered at A, centered at t0, centered at t0, I'm taking an interval, small interval, so A is a very small number here, from t0 minus A to t0 plus A, t0 minus A to t0 plus A. And I'm going to take a value of function to be 0 on left hand side here, 0, 0 on the right hand side. Okay, and on the middle, I'm going to take a value of function to be 1 over 2a, so that the reason why I take the value of the function between this interval as 1 over 2a is that I want to make the area under this curve or under this graph to be equals to 1. Okay. So whenever I choose, whichever value I choose for a, I make the integration always equals to 1. So if I choose a smaller a, suppose that my a is right here, then the graph of function looks like this. So it's higher and higher as I make my a smaller and smaller. So my direct delta t, sorry, this is a typo. So this is a delta t minus t0. Okay, so I'm shifting to t0 point. So delta t minus t0 is a limit of delta a when a goes to 0. So what I'm doing here is I'm getting my a smaller and smaller and make this rectangle thinner and thinner but higher and higher. But I'm not really looking at the actual limit. So that's a tricky part. So it's also not very rigorous in mathematical terminology, but it's very useful method when you make a system in engineering or physics and try to solve the system using the Laplace transform, because what you're trying to do is trying to approximate what happens in the very short period of time with a certain amount of energy as a graph. So suppose that you're hitting a ball with a bat. So of course there's a small amount of time interval that the bat is touching the ball and ball is a little bit bending, and then after that short amount of time the ball is leaving, ball is detached from the ball and then flying through the air. But however, this whole process is happening in an instant moment. So you can assume that this hitting the ball happens in a very short amount of time. So what I'm trying to do is trying to get trying to get this situation in one simple graph as delta t, assuming that this A, where this t0 is the moment when the bat is hitting the ball, and t0 minus a to t0a is somewhat in between that moment when bat is hitting the ball, where the transfer of the energy from the bat to the ball is happening. So I'm trying to get this situation in a nice mathematical graph, but in real life what happens is here, so we have this sharp transfer of energy or burst of energy, but I'm trying to approximate this graph using somehow this delta A function. So and trying to exaggerate by sending A to 0. So if A actually goes to 0, then everything is 0 except for t0. So that's not the case we're actually considering. We're assuming, by this limit notation, we're assuming that A is very, very small, not actually equals to 0. Okay, so here's a proposition. We can take a Laplace transform of direct delta function. So if we take the direct delta function, then the Laplace transform is e to the minus t0s. Okay. So there's no formula such as simply obtaining e to the negative st. So if you're looking at the previous formula, there's no formula that gives the result as e to the negative st here. So whenever you have Laplace transform and obtained this exponential function, then you can get this. You can think about this original function as a direct delta function. Okay, so if we have time, we are going to derive this formula. But for now, let's move on. It's more important to know how to apply this formula to the real problems. So now, from now on, we are going to write this Laplace transform of f of t simply as large f of s. Okay. So then, if you have an exponential function multiplied to the original function, then the result is the shifting of Laplace transform. Okay. And if you have a Laplace transform of power function times the original function, then it becomes the derivative of original function. Okay. And we have a sign change depending on the parity of n. So let's try to take a Laplace transform of these two functions. Okay. So everything might be confusing. So I'm going to give a very detailed computation, and don't worry about memorizing the formula. Either you automatically memorize the formula by solving many examples, or I will give the formula in the midterm test, final test. So you don't have to worry about forgetting or confusing the formula, but you need to understand how to apply the formula. So let's take the Laplace transform of t times e to the negative 2t. Okay. So there are two methods of Laplace transform of this function. So if you're looking at the proposition 2, in the second statement of the proposition 2, this says that I can take e to the negative at, this formula, so e to the at times f of t equals to large f of s minus a, or if I use this formula, then my f of t becomes t and a becomes minus 2, right? Or you can use the other formula, this formula, the third statement in the proposition that says t to the n of ft is equals to -1 to the power of n dn ds of f of s. So in that case, you have f of t equals to e to the -2t, and n is 1, right? There are two ways of finding Laplace transform, and it gives the same result. So apply this formula. So we have t as the original function. So the Laplace transform of t is, so I erased it. It's so s of s to the 2 of 1 factorial, right? I don't even memorize the formula, so I have to keep looking at. So at t of 1, yeah, that's right. So, and then that's our f of t. So let me write it here. So f of s is 1 over s squared, okay? But I'm not using this as a result. I have to shift it by -2. So I have to change this to s plus 2 squared. So originally I have to take a negative minus of -2, but it's a plus 2. And how about I'm using this formula? So we have -1 to the power of 1. Give a little bit of space here. And then take a derivative, first order 1 derivative of f of s. And f of s is the Laplace transform of exponential function. And what was the Laplace transform of exponential function? It's 1 over s minus of -2, so it's plus 2, right? So therefore, take a derivative of 1 over s plus 2 and take a -1. And we have s plus 2 squared of -1, but I have -1 already here, so it's a plus 1. So I have a same result. Okay? So how about the second example? We have sine and cosine and hyperbolic sine multiplied. So if you have any question here, let me know. Cosine t, sine ht. So how do you take the Laplace transform of these product? So first of all, we know what the Laplace transform of cosine, and we know what Laplace transform of hyperbolic sine, but we didn't say about the Laplace transform of f of t times g of t. So I emphasize again, many students, lots of students make a mistake about Laplace transform when you see this kind of Laplace transform using this formula, not a formula, but I believe that this is a formula for some students. So some students believe that this is a formula. If you have a product of two functions and Laplace transform of products, then Laplace transform of each functions. This is not a formula, okay? There's no formula such as this. So this is not a formula, okay? Do not use this. Use only the formula that I gave you. This is the entire formula of Laplace transform. So don't make up a new formula. So how do you solve this Laplace transform? Oh, yes, expand which one? certainly I cannot expand cosine, so you have to expand hyperbolic sine. So this is equals to cosine t of 1 over 2 e to the t plus 1 over 2 e to the negative t. So, and then by the first proposition, its Laplace transform is linear, so this is equals to e to the t cosine t and plus 1 over 2 L e to the negative t cosine t. So now we only need to use this formula, right? So there's no other formula to use. So our function is cosine t in the first Laplace transform, and the Laplace transform of cosine t is s over s squared plus 1. So we have 1 over 2 s squared plus 1 to s. But now we have e to the t, so I have to shift it by 1 to the right. So I need minus 1 everywhere. Okay, so that's the first. And second, we have 1 over 2. And we have a negative 1 instead of plus 1. So everything is same except for I replaced negative 1 to 1. So we have s plus 1 squared plus 1 and s plus 1. Okay. So you can combine these two if you want, but this is the result. Okay. Any questions? Okay, so now we are ready to talk about application to differential equations. Questions on the first one. So it's not there's no order. So this is a two-way of solving this Laplace transform. So the same Laplace transform can be solved by this proposition, first proposition, second, I mean the proposition 2, or proposition 3 in the second method. But both methods give the same result. So I'm telling you that there is no unique way of solving Laplace transform. Sometimes there is a unique way like this one, but many times you can solve Laplace transform in a different method. Is that answers the question? Okay, so let's talk about the inverse Laplace transform. Was it sine? Oh, it was sine. Thank you for correction. Yeah, that was sine. So sine h minus. Yeah, thank you. So, well, as a side note, in the MATLAB, there is a tool, there is a command that does the Laplace transform. You don't have to do the Laplace transform by hand. But the bad news is since we are going to take an offline final, we're not able to use the MATLAB. So you have to do the Laplace transform by your hand. Okay, but when you do the homework, please check your answer using the MATLAB. Okay, so although you have to write the process of taking Laplace transform, but you can check your answer, final answer, whether it's correct or not using the MATLAB. So I will show you the end of the lecture how to use it. So let's take a inverse Laplace transform. So after you take the Laplace transform, it's a function of s. So I'm going to find out which original function was used to obtain this function of s. So suppose that we have given by this rational function of polynomials in terms of s, and I want to find the inverse Laplace transform. In other words, if I take this as f of t, then it means that the Laplace transform of this f of t is given by 6s squared plus 50 divided by s plus 3 s squared plus 4. Okay, so same as for Laplace transform, Laplace inverse transform is also linear. This is also linear. So therefore, I need to split. I need to decompose my f of s into the terms that I can find the inverse Laplace form easily by previous formulas of Laplace transform. So I'm going to split my denominators, s plus 3 and s squared plus 4, and s squared plus 4 can also further divide it into s terms and constant terms. I intentionally used my constant term to be 3 times 2 instead of 6 times 1 because I want to use the Laplace transform, inverse Laplace transform on here, here, and here. Okay. So think about 1 over s plus 3. This is the Laplace transform of e to the negative 3t. Okay. So if you're looking at the previous formula here, this is the formula. Okay. Then also think about the s over s squared plus 4. This is a Laplace transform of cosine 2t, right? And here we have, it's a Laplace transform of sine 2t, right? So therefore, you can assume that this is the Laplace transform of these series, some of these functions, okay? So it's like a subtraction. If you learn the addition, you have to learn the subtraction, okay? And also, it's not hard. All right, so now this is the main point, because if we want to solve the differential equation, there is a derivative terms in the equation. So you have to know how to take a Laplace transform of derivatives of the function. So suppose that your function is continuous until you take the nth order derivatives on this positive interval. Now, what's the Laplace transform of nth order derivative? It's given by this function. So first of all, you have to take a Laplace transform of original function f of t and then multiply with s to the power of n. And then there's a polynomial terms depending on the value of derivatives of each order, and you take the negative of the s to the n minus 1 with the coefficient f0. So this is the order 0 derivative. And then take a negative of s to the n minus 2 times f prime 0. So this is order 1 derivative. And later you take the s to the 0 times s to the 0 is 1. So that's why I omitted here. Times the order n minus 1 derivative at 0. Okay, so you see if you add the degree of powers and the order of derivative, it's always n minus 1. Okay, number of degree plus number of order is always n minus 1. So if you memorize or don't confuse interpreting the formula, memorize this method. So you take this term, and then the rest of the term is negative of these terms satisfying this property. Okay. Let's see the example here. So this is the very standard example that uses the previous examples of inverse Laplace transform. Let's suppose that we have this formula, this equation. So whenever you want to use the Laplace transform, the equation must provide it with the initial value condition. So very important. If you want to use the Laplace transform solving the differential equation, your differential equation must be provided with the initial value condition. The initial value condition must be at 0, okay? Always at 0. Now, let's assume that large Y, usually we use the large capital terms for Laplace transform, as a Laplace transform of small y, and use the Laplace transform on the left and right hand side. So on the left hand side, we get Sy, because we have an order 1 derivative and n equals to 1, minus y0. So this is the order 0 derivative and times s0. So the only one terms appears as a negative terms. So this is the Laplace transform of y prime. And 3y transform into 3 large y, obviously. And this term becomes 26 over s plus 4, s squared plus 4. Okay. Now, if you simplify ys, then we plug in y0 equals to 6 here. We get this formula. Just make it simpler. So then what you get is inverse Laplace transform to retrieve the original function yt. So we already done the inverse Laplace transform of this function, so yt is given by this function. Okay? Does it make sense? Do I have a lot of examples? Okay, let's move on, and if we have time, we will see the examples. So now, this is the formula that I also want to emphasize. If you want the result of Laplace transform as product of two well-known results of Laplace transform, then original function should not be the product of two functions, but it's a convolution of two functions. What is the convolution? So convolution of f and g is denoted by this asterisk here instead of dot, because dot represents the product, as this integral of f of tau times g of t minus tau. Okay. So the reason why it's called convolution is that you take 0 to t and integrate your t from here and integrate and multiply your function g from this direction. Okay, so suppose that your function f is given as these functions, and your g of t is given by this function. So you're simply looking at the functions on this interval, and then try to multiply your function f of t from this direction and g of t to this direction, and then integrate from 0 to t. So when tau becomes t, then gt, your gt is at the position where 0, and f tau goes to the t. So this is a convolution. And only when you take a convolution, the Laplace transform becomes the product of Laplace transform of each function. So for example, so this is the application of this formula. When you take g of t equals to 1, then you only have an integral of f of tau, because this term is always 1. So you can take a Laplace transform of integral of the function, or in other words, antiderivative of antiderivative. So then you get this function. So this 1 over s comes from the Laplace transform of 1. Okay, and this Laplace transform f of t is given by the specific function f of tau. So let's look at the examples here. So we have a function defined to be the somehow recursive formula, because we have an integration inside of the definition of function. Now you can transform this as a derivative, a differential equation, because if you take a derivative, what happens on the left and right hand side is the f prime equals to 6t plus e to the negative t minus of f of t. Sorry, I think it's hard to take a derivative of this one. So we have t inside here. T. All right, you just take out that t. So we get d dt of e to the t of dt 0t f of tau times e to the negative tau dt. So in either way, it's hard to take out this integral here, because now if you take the derivative of this, first take the derivative of e to the t, so you get negative e to the t of integration something, and then minus of e to the t of derivative of integration. Then now we have f of t times e to the negative t, so this disappears, but still you have a integration sign here. So in either way, this equation cannot be turned into the differential equation that we already know for the solution. So what we have to do is using the Laplace transform, and this is already given by convolution of f of t and e to the t. So use the formula as follows. So you have a Laplace transform of small f as large F, and then Laplace transform of power function and exponential function as this. And this convolution becomes the product of two Laplace transform. One is the Laplace transform of f of tau, which is f of s, and other one is Laplace transform of e to the t. Okay, not e to the tau minus t or e to the t minus tau, because this already is given as g of t minus tau in the original formula, and we are going to take a Laplace transform of g of t. Okay, not g of t minus tau. Okay, so this is the Laplace transform of e to the t. Okay, so and then let's combine f of s, and then rewrite this f of s only in terms of s. Then take the inverse Laplace transform. What happens to 6 over s cubed? We have s, so 6 over s cubed is s 2 plus 1 over 2 factorial times 3, right? So this is the Laplace transform of t square, okay? And 3 is multiplied as a coefficient, so we have 3 here. And then do the same thing for other factors. So this is our result. So if you replug in this formula into the this equation, and you see this is a solution to this equation. So sometimes you need an integral equation, not the differential equations. So that's also the upshot of this Laplace transform. Now, well, let's take the inverse Laplace transform. I don't know why the example appears here, but let's take it. So how do you take the inverse Laplace transform of this function? So you might notice that this is a product of two functions, or you can split these two functions. So similar to Laplace transform, inverse Laplace transform also has several methods. So you can either use, let's say, s 1 over s squared. Sorry, 1 over s squared. A s squared plus a squared, and then now you can use the convolution that f of t and g of t is given a certain way. Then the Laplace transform of gt t gt tau. Sorry, this is tau. T minus tau, d tau becomes f of s times g of s. So I set this f of s to be 1 over s squared and g of s to be a over s squared plus a squared. Then what will be the f of t if I have f of s as 1 over s squared? It's t, right? And what about g of t? It's a sine a. Sine at. So what's the result? So this was the result if I take the inverse Laplace transform. This is integration from 0 to t of t times, tau times sine a t minus tau d tau. Okay. That's a one result. That's only one result. Is there any other way to solve the inverse Laplace transform? Is there other way to find different result? You can split this denominator, right? So s squared plus a plus s squared plus a squared plus b, and now becomes s times s squared plus a squared, a s squared plus a squared plus b s squared, and I want this to be equals to a s squared plus a squared, right? Then my a must be 1 over a and b must be minus 1 over a. So rewrite the inside here. We have 1 over a times 1 over s squared minus 1 over a times 1 over s squared plus a squared. And by linearity of inverse Laplace transform, I can split this 1 over a times inverse Laplace 1 over s squared minus 1 over a times inverse Laplace of, let's take a instead of, so I put this a squared here, a squared plus a squared. Okay, so that's what's the result. So 1 over a times t minus 1 over a squared of what? Sine t, sine at. Now you see, I had this integration as a result of inverse Laplace transform. If I use this formula, if I use other formula, I got this formula. I got this result. Which one is correct? Which one is correct? Yes, they're both correct. They're both correct if you compute it correctly. So here both correct. So you have 0t of tau sine t minus tau d tau is equals to, where's a? Oh, a is here. A is equals to 1 over a t minus 1 over a sine at. They are same thing. You can check by your by integration by parts, or you can believe it. All right. So I think the rest of the parts are unnecessary to find to do the homework. But let's do the examples for the rest of the time. So let me look at the book here. So I'm going to do some other give an example, some other examples of a plus transform. Plus transform. Okay. Some might be homework problems. I don't know. I don't remember exactly what homework problem was, but I'm just taking some example from the textbook. And I selected some problems from the textbook. Okay, so here's the... Okay. All right, so I want to do some interesting questions. So let's take this one, s minus 1 s squared e to the negative s. How would you take the inverse Laplace transform? So obviously this is simply make this worse. Let's split this. So inverse Laplace of e to the negative s over s minus e to the negative s over s square. Okay. And then what? So whenever you have multiplication of Laplace transform, multiplication of two functions in terms of s, the convolution is the last formula that you have to use. Try other formulas. Try the formulas before the convolution to find the inverse Laplace transform. So let's look at the formula which contains the e to the negative as. So let's see. Wait. Where was the e to the e to the negative s? Oh, here, yeah. So if you're looking at this formula, so whenever you have e to the negative as applied to the original some function of s, then you have to considering that this original function is applied with the unit step function, right? So let's use this. Laplace transform of t minus a ut minus a is e to the as of fs. Okay. So let's take it separately here. So we have e to the 1s, and f of s is 1 over s, right? So if f of s is 1 over s, then what's the original function? It's 1, right? So I want to take the shift of 1, but it's already 1. So 1 times of u of t minus 1. So that's the first part. And how about the second part? So if f of s is 1 over s squared, then f of t is t, right? So you're going to take a shift of t by 1 and then multiply t minus 1, right? Now, how does this function look like? Just for your information, let's try to draw this function. So you can combine these two because it only has u of t minus 1. And then you multiply this, you get 2 minus t, right? So 2 minus t, it looks like this. You have 2 here. And then this is y equals to 2 minus t. But original function is multiplied with u of t minus 1. So when t is less than 1, it's 0. But when t is bigger than 1, now it's behaved like 2 minus t. So this is the function. This is the graph of function. Original, this function, like inverse Laplace transform. Okay. Okay, let's do this one. How about e to the negative t minus t over 2 u of t minus 2? How do you take the Laplace transform of this? So first of all, if you want to use the formula, this is not the correct formula because this correct formula always contained as f of t minus a, u of t minus a. Here a is 2, so the t must be always written as t minus a. So here we only have t. So let's try to match our given formula as this formula. So we have e to the negative t minus 2 over 2 times u of t minus 2. But now, since I replaced t by t minus 2, the function changed. It changed by adding plus 2 here, right? So plus 2 over 2, so it's plus 1. So I have to subtract 1 here again in order to make as t e to the negative t over 2, right? So I have some constant terms appeared here. So we have 1 over e times e to the negative t minus 2 over 2. So it's basically 1 over 2 times t minus 2 u of t minus 2. Okay, so then we can use the Laplace transform. This is equals to e minus f of s. So it's e to the negative 2s of Laplace transform of what? So this f of s is a Laplace transform of f of t, where f of t, this guy is a shift of f of t by 2. So original f of t is e to the negative 1 over 2t, right? So I have to take the Laplace transform of this function. So this is s minus 1 over 2, 1, right? So this is s plus 1 over 2 e to the negative 2s minus 1. So I just combine this e. So this is our Laplace transform. Okay? These are practice, but let's see the hardest one. I leave my hardest one to the final exams. So I will show you. Okay, so let me explain the graph here. So this one, I'm graphing. If I made a mistake, please let me know. So I'm graphing this function, okay? So originally, I have a multiplication of two functions. So this function 2 minus t is graphed as follows. So 2 from 2, it decreases by slope 1. And then multiply with this step function. So basically, step function is 0 or 1, right? At 1, it changes the value. Now, so I'm applying this, the white one, multiplying white one with the red one. So until 1, so I don't even care about when t is negative, so let's erase this. So when t is less than 1, it's always 0, no matter what the value of red line is. But after 1, it's already 1, so I'm following the graph of the red line exactly here. So we have starting from 1 and decrease by slope 1. Okay, so let me show you my home website. So here, here. Sorry. Okay. So this is my website. Here's my address. I pasted on the LMS chat. So if you go to SE101, there's a past exams, and let's look at spring final. Where's Laplace transform? Okay, not this one. So I want the questions which ask a Laplace transform only. Okay, so let's hear. Okay, also easy ones. So let's look at C, this part. Let me enlarge this. So let's try to do this Laplace transform, the part C of number 10. So everyone got this one. So let me change to Blackboard. So inverse Laplace transform of some weird function SE minus S S squared 4S plus 2. Now, this is not a perfect square, okay? So S squared plus 4S plus 2 is not a perfect square. How do you change so that I can use the Laplace transform? So it still is a square. So let's try to use 4S plus 4 minus 2. SE minus S. You see how I'm doing? So then what? I'm going to make this as a perfect square. S plus 2 squared minus 2. S times e to the minus s. Now it's get something, right? It gets something. But still, well, in order to apply the formula, I need a square here. So it's a square of square root of 2. So I get s plus 2 square minus square root of 2 square. So this serves as a k square in the formula of sine, hyperbolic cosine. Now, what happens to s? So I have a s plus 2 instead of s in the denominator. If this were s, that's okay, but now it's too different. So I need s plus 2, e to the minus s. But if I change to s plus 2, I added 2 more s, e to the negative s, so I have to subtract it. Okay? So what happens? We have inverse Laplace transform of s plus 2 e to the negative s plus 2 square minus square root of 2 and minus 2 times e to the negative s and s plus 2 square minus square root of 2. Right? So what's the first one? So we have something that's similar, something that we know, times e to the negative s. So whichever we have, if we multiply these, then we get step function, u of t minus 1 times f of t minus 1, right? And here, f of t is what? This is our f of t, s plus 2 square minus square root of 2. Okay? How about here? We also have e to the negative s multiplied to, in this case, let's take out this square root of 2, these, right? So this is negative 2 times g of s times, what am I doing? So, so it's just f, small f. So this guy is large s, f of s. So this guy is f of s. I'm taking this guy as g of s. And then u of t minus 1, g of t minus 1. So here gs is given by square root of 2, s plus 2 square minus square root of 2s. Okay? And what's ft and gt now? So this f of s is, I run out of the symbols here. So let's say f of 1 here. It's a shifting of f of 1 by negative 2, right? There's no formula that I can use directly to here. It's a shifting of something where this f of 1s is now s over s squared minus square root of 2 squared, right? So the reason why I use the shifting is there is a formula when I shift the function. So here. You see, in the second proposition here, we have the result of e to the at ft is the shifting of the Laplace transform. So I'm going to use that. Okay. So what is f of t? So f of t is inverse Laplace transform of f of s, but it's an inverse Laplace transform of f of s minus 2, okay? And that's equal to what? That equals to what? E to the, so I'm using this formula, EAT FT equals to F of S minus A. But I'm using it to F1, so my inverse Laplace transform gives the F1 function. So e to the minus 2t times f of 1t. Now what's f of 1t? F of 1t is an inverse transform of large f of 1. So f of 1t, the inverse transform of f1 is what? What's the inverse transform of this? There's a little bit of delay, so I will wait. Right, yeah, cosine inverse. We have 3 different answers. Yeah, cosine, yeah, hyperbolic cosine. This one, so you see the fourth proposition, we have a cosine h, kt equals to s over s squared minus k squared. So that I'm using that. All right, so this is equal to cosine h square root of t. So this guy is equals to cosine h square root of t, right? And then that's the result of inverse transform of f of s, but what we have to do is plug into this formula by shifting that function again. So this whole thing becomes u of t minus 1 times the shifting of these function, e to the negative 2 t minus 1 cosine h square root of 2 t minus 1. That's the first part. Minus 2 times of ut minus 1. And then you do the similar thing with this guy. So everything is same except that we have square root of 2 instead of s plus 2. That means we use sine h instead of cosine h. So we have sine, same thing with the sine. E to the negative 2 t minus 1 sine h square root of 2 t minus 1. Right. So it's not simple, right? Okay, so for the rest of the time, I will do the MATLAB, but is there any questions? So frankly, I'm not going to test you by giving the hard Laplace transform or hard inverse Laplace transform, because most of the Laplace transform, or every 100% of Laplace transform can be done by MATLAB. So it's important to know how to get the right result, not how to get the result by hand. Okay. Of course, you have to understand the formula, but outcome is important. Okay, so here. Okay, let me go back to the question here. Basically, let's review again. So we have inverse Laplace transform. I transformed this formula into something that I can take inverse Laplace transform. And then I think you already understand this formula, how I obtained this formula. But the way I get this is I already know that this formula works for inverse Laplace transform. So, and I also had an intuition that this formula has to be transformed so that I can take this Laplace transform. So anyway, now first of all, I split these parts with exponential term. Whenever exponential term is applied to the inverse Laplace transform, then the result is the unit step function multiplied to the original function. Now, original function f of t, not f of t minus 1, f of t is an inverse transform of these parts. Okay, these whole entire thing is f of s, not s. It includes s plus 2 here. Okay, so I need to take an inverse Laplace transform of these. Now, but you see, this is a shifting of more simpler form, f of 1, right? So when I shift my function s, function large f, then the inverse transform is applied with the e to the at. So I'm using this formula. So my result function, the original function f of s, is a shifting of f1 by -2. So the original function, I mean the f of 1, is given by the Laplace transform of cosine h. F of 1 is a cosine h squared root of 2t. So therefore, if I take the Laplace transform of this function, then using this formula, it's e to the -2t times cosine h squared root of 2t. So now I have to plug this ft into this formula by shifting again by 1. So I replace t by t minus 1 everywhere. We have t minus 1 and t minus 1. So that gives the first summand. And for the second summand, everything is same except that I use the, after all, I have to use the hyperbolic sign instead of hyperbolic cosine. So my g must be the same formula except that I have hyperbolic sign. So I have hyperbolic sign and everything is similar, but I have a -2. I have negative square root of 2 as a coefficient. So that's the result. You can do the same thing with the second summand following the same procedure. Any other questions? Okay. All right. Okay. So here, Laplace transform. Frankly, I have to search for it again. Laplace transform. MATLAB. 여기는 한글로 할게요. 잠깐만요. 왜 이래? 네. 이게 심볼릭이어야 되는지 아닌지 내가 헷갈려가지고 지금 찾아보는 거거든요. 오케이. 심볼릭이어야 되네요. 오케이. 자, 일단은 sims ts를 하나 정의를 합시다. 아까 했던 거 한번 찾아볼게요. 뭐가 좋을까? 아까 했던 것 중에 아까 인버스만 했었나? 그냥 라플라스 한 게 그냥 코사인 t랑 간단한 거 합시다. 코사인 t 하고 라플라스 f 그냥 이게 나오죠. 원래 공식 나오잖아요. 인버스 라플라스 해봅시다. 인버스. 여기서 large f를 아까 방금 봤던 거 해볼게요. s exponential minus s 나누기 s square plus 4s plus 2. 이거는 지금 심볼릭이기 때문에 점을 안 붙여도 돼요. 그 다음에 I 라플라스. 잠깐만. 4 times s. 이건 해야지. 보시면은 heave side라고 돼 있죠. heavy side. 그러니까 우리가 저는 그냥 스텝 펑션이라고 했는데 정확한 명칭은 heavy side 펑션이에요. 그러니까 u라고 생각하시면 돼요. 요 heavy side는 u times t minus 1 exponential 2 minus 2t. 그러니까 여기서 이제 minus 2 times t minus 1 이걸 새로 쓴 거예요. 그렇죠? 그다음에 cosine square root of 2 t minus 1 맞죠? cosine h 하고 뒤에 거는 이제 square root of 2 times sin 하고 그 다음에 이거 하고 exponential 요거는 똑같이 나왔으니까 heavy side랑 같이 묶어가지고 요 안에 다시 쓴 거예요. 그러니까 여러분들 풀고 손으로 풀고 그러니까 과정은 있어야 되니까 손으로 풀고 한번 체크해 보세요. 요 답을. 잠깐만요. 제가 매틀랩으로 heavy side를 하는 방법은 heavy side 다시 한번 좀 봐야 되겠는데 그냥 이렇게 하면 되는구나. 그냥 heavy side로 쓰면 되는군요. 여기 예를 들어 가지고 f를 heavy side t-2 곱하기 xt라고 해봅시다. 자 그러면은 라플라스 f 했을 때 이렇게 나오죠. 자 우리가 heavy side t-2 하고 exponential exponential을 하면은 원래 라플라스 트랜스폼 of exponential 하면은 1 over s over a가 나오죠. s minus a가 나오잖아요. 근데 이제 지금 t-2를 했을 때는 그냥 깔끔하게 나올 거예요. 자, 지금 여기 보면은 exponential minus 2s 요게 이제 heavy side 때문에 나오는 거고 이제 지금 exponential의 개수가 1이기 때문에 s minus 1이 나왔죠. 1 over s minus 1이 나왔죠. 근데 아까는 제가 요거를 뺐잖아요. 요거 뺐잖아요. 그죠? 그러니까 요거를 빼면은 얘는 뭐랑 같냐면 얘 곱하기 exponential minus 2 요거랑 똑같은 거예요. 두 개 합쳐야 되니까. 그렇죠? 아이고 이렇게 하니까 또 이게 참값이 안 나오고 이렇게 되네요. 근데 여하튼 간에 우리가 heavy side ut-2랑 뭔가 곱해져 있으면은 공식 적용하실 때 이 함수, 요 뒤에 나오는 함수를 똑같은 그 거리만큼 shift 한 걸로 고쳐줬을 때 이제 원래 함수랑 맞아지도록 이렇게 뭐 나누거나 빼거나 이렇게 맞춰준 다음에 라플라스 트랜스폼을 해야 돼요. 그러니까 바로 여기다 적용하시면 안 돼요. 그러니까 여기 보면 지금 exponential 2가 곱해져 있잖아요. 아까 t-2 했던 것보다 exponential 2가 더 곱해져 있단 말이에요. 거기 그대로 나와야 돼요.